Hello everybody, today I want to share with you an update for my Jupyter notebook that connects Prosper and Openserver using Python. Okay, so I am going to restart the Jupyter notebook. Okay, here I have my Prosper model. So I will import the libraries. In this section you can select the distribution for your variables. You can use constant, uniform, or a normal distribution. You can set up the values. I am going to change the reservoir pressure. I am using here a uniform distribution. Okay, so I run this cell. I get a dictionary that contains all the values for each variable to calculate the distributions. Okay, so here I have a function that plots all the distributions. Here you can see the plots. It's easier to see. Then you can import your production test data if you have. You can change this. It depends on your data file. If you have spaces, you can use a different delimiter. Okay. In my data, gas production is in 1000 cubic feet per day, so I am dividing by 1000 to get million. I am just checking the data. Here you can specify if you want to use the chokes in your production test data, or you can specify the choke. I am going to change it here to 28. So you have information here. Your production test chokes from your data are 18, 16, 14, and 20 in this case. I am specifying 28. If I change this variable here to true, the code will use the production test chokes, but I am going to use only one choke, 28. Okay, that's why it says chokes to be used on Prosper is only 28. You can pass a list also if you want. Here you select the correlations. You can see my previous videos to see how it works. This is only a test how the correlations are going to be used in Prosper. And the new update has these two functions. This one is to generate the values for each variable, because all the data is in this dictionary. I can go to the dictionary and get the data, so it's easier. So you can see here is the dictionary, the variable name, and the value in each variable. Depending, this index will tell the code. Okay, here is the mean, here is the standard deviation, etc. Also, here is the check for the perforations. It never can be more than the reservoir thickness, so this condition makes sure you don't get perforation values higher than the thickness of the reservoir. Okay, I run. This function is only to print the values. and I am going to do only 300 iterations, so it doesn't take too long. See, I am calculating for choke 28 using distributions for each variable, using different correlations. I am getting the solutions, the wellhead pressure, the AOF for the reservoir. It's finishing. Okay. Now I am saving everything on dictionaries here. See. Before I had more dictionaries, so I decided to reduce because it's easier to see where the data is. So I only have one data frame for BLP and IPR that data. Also, all the input values are in this data frame, and I have two additional data frames that contain the input with solution and the input without solutions. Okay, so I can look for the variables that are impacting the production of the well. So here you can save, you can import results if you have files you have saved before, and then I can check the values for all the data frames, all iterations, only solutions. Here you can see only solutions and no solutions. Okay, and also the statistics for all my data frames. Okay. Also, I have this additional check to make sure my perforations are not bigger than my reservoir thickness. So the minimum value should be 0. If you are getting negative values, something is not working, but just run this cell to make sure. Okay, then this one is just to see the distribution for all iterations and iterations with solutions. You can see here the difference, density map showing the history from production test and the PROSPER solutions. Okay, all the iterations, pressure versus gas rate, also only the solutions, just to see how the model is performing. And this plot is another way to view the solutions, the distribution, the cumulatives. Maybe you don't need it, but it's there because here you can see everything. Okay, and then here you can see the iterations for all the correlations, and also the black section shows no solutions. So you can see the correlations with index 5 and 9 have the most results without solutions. 5 and 9 are Bex and Brills, and 9 is Orkisewski. So then viewing this, you can maybe select another correlations or check what's going on with those correlations. Okay? More data for the correlations. Here you can create a density map for each correlation and check how correlates with your historic data. See? And that plot is very nice to check how your model is performing for each correlation. Here you can clean your data if you have outliers over here. Let me see, over here maybe you see some very big values. You can clean them here. just selecting the percentiles, minimum and maximum, but I am not going to use it. Then before I had those plots separated in different cells. Now I have next to each other each variable, so I can compare easily. And also next I can plot the same plots, but one in the same plot, no solution and no solution. And visually I can see which are different, especially in the cumulative distribution. See, for example, reservoir pressure is very important. It's impacting above maybe 4,200 psi. I have no problems, always producing. Below 4,200 I am having no solutions. So with all these conditions, water gas ratio, skin, perforation, permeability, below this reservoir pressure I am having problems. So I have to check how my well is going after this reservoir pressure. And here you can see the difference visually, but if you want to calculate if the distributions are different, you can use this test. And here you get in yellow which are different. Reservoir pressure, we saw here, it's important. Top pressure, water gas rate is not very important, maybe because we are using a water gas rate from 0 to 500. If we increase the maximum limit for water gas rate, maybe it will get important. Let's go back. Okay, here. For solution gas, flowing bottom hole pressure, and solution wellhead pressure, you will get 1 or close to 1 always, because they are calculated, so it's not very meaningful, these values. Okay, now you can create cross plots for all the inputs, just to check how the correlation, what correlation you get with all the solutions, with all the iterations, but it has no meaning because it's affected by the non-solutions. So this is the real correlation plots, because here you don't have the no solutions, only solutions, and you can see the negative correlation for the water gas rate, a little bit positive for reservoir pressure. Okay, then you can go, this again is visual, you can see the correlation, how it goes, but you can also calculate the correlation coefficients. Okay, then see, here you have the correlations. The most important correlation is water gas rate. This variable is affecting very much the productivity. Let's see here, water gas rate. See, for small values below maybe 100, 150 barrels per million cubic feet, you have no problem producing, but after that you are getting some no solutions, so that's what you expect. When you produce water, you start to decline the production. Okay, so here you can get which variable is more important. Here, water production, then reservoir pressure, top pressure maybe. Then you can plot the IPR BLP data. Here I added a widget, so you can see all the results here moving this slide bar. Also you see, for example, here you have the solution. It's 6 million cubic feet per day, the pressure solution, and also you have the inputs for this iteration. So for this iteration